We're going to talk about a semi-classical approximation. Not the semi-classical approximation, because there are actually hundreds of different variants with various levels of subtle differences or perhaps even major differences. But we're going to talk about a very simple and easy one that lets us deal with quite complicated many-body quantum systems and get a surprising amount of physics out while throwing away large amounts of the interesting possibilities of the quantum state. The first thing we're going to do is we're going to assume that the quantum state completely factorizes. So a completely general state has an independent coefficient, complex number coefficient, for every different combination of numbers of particles in the single particle states. But when we assume it factorizes, then we assume that these coefficients can be factorized. So in other words, we should be able to reorder this sum to be simply the tensor product of all these things. This is perhaps a little bit over-prescriptive because each of these coefficients might actually be slightly different for each mode. So we'll say we've got a set of coefficients Cj for the jth mode. We're then going to assume that each of these states is a coherent state. So a coherent state is characterized by a single complex number, in this case beta, and it's just a linear superposition of the number states. All states have to be because the number states are a basis. So in some sense it's as simple as that. The reason coherent states are quite useful is that they have this particular property that they're the eigenstate of the annihilation operator. And in fact, that complex number is just the eigenvalue. Now that's very easy to show. You simply apply the annihilation operator to that state and that'll drop out. So our semi-classical approximation goes from having a completely arbitrary many-body quantum mechanical state through to one that is a tensor product of a bunch of coherent states. This tensor product is over all the possible modes it can be in. If there happens to be a continuous index, it's just a continuous index. So that might look something like, so it looks a little bit like a wave function here. So our index looks a bit like a wave function simply because it's a complex number for each point in space. Just like here we had a complex number for each single mode. So actually the dimension of our semi-classical space is about the same size as the dimension of a quantum system for a single particle. So that's an extremely strong approximation. We've got spatial structure there, but we've lost all the ability to have entanglement between different modes of our system. But it is also very easy to make calculations. Supposing we have some kind of expectation value we want to calculate, then when our state is this coherent state, it's a lot easier. So when we apply this field operator to this state, if we apply it to that state, just looking at it, you can see that when we apply the field operator at y to the yth state here, we're going to get an eigenvalue coming out. Now crucially, this is not an annihilation operator anymore, that's just a complex number. So we can take that out of the expectation value. Now we can't do the same thing for here, because although the coherent state is an eigenstate of the annihilation operator, it's not an eigenstate of the creation operator. So what are we going to do here? We're going to consider this acting backwards. So in other words, the expectation value of these field operators is exactly equal to the product of the complex numbers in the coherent states. And the annihilation operator simply gives us the eigenvalue from the coherent state, and the creation operator gives us the complex conjugate of it. And we could do the same thing for long strings of creation annihilation operators. All we need is all the annihilation operators on the right and all the creation operators on the left, and that will work. And if you want to calculate something that doesn't have that, and that ordering is called normal ordering, we have all the creation and then all the annihilation. If you have something that doesn't have that, then you just use the commutation relations to rearrange them. Now this semi-classical approximation has another name. It's also called the mean field approximation. And the reason for that is very easy to explain. If we look at the expectation value of the field operator, then of course we're just going to get a single complex number from our coherent state. And so in some sense, our complex number, this parameter that we're using to parameterize our quantum state, is the average of the field, in the sense that is the expectation value of the field operator. So it's called the mean field approximation.